Today, my icebreaker for this talk is three sounds. The first sound is like this. This is called 1F noise, pink noise, that commonly encountered in our semiconductor circuits, right? Especially like high K noise from the defects. This one is a little bit not that bad, right? Pink noise. It's not like violent noise. And let's check another noise. This is a funny noise. This is called this kind of dripping noise, the drooping noise. It's one of the most critical and famous noise in the semiconductor world, especially in the advanced one. It happened also in RF, but we borrow the idea. It's about the noise from the power transients.
You pull it sharply out of the pot.
And this is the mandrake noise, that is the shrieking sound made by this legend myth mandrake, right? We saw it in Harry Potter. Very cute but very noisy stuff. You had to wear this ear muff, right? You had to wear this ear muff to fend it off. Okay, so that's an icebreaker of today. Hi folks, today I would like to continue my talk about the magic of semiconductors, chapter 13 this time, and then also include the packaging process technology, chapter 17. And you have, at least you have heard the icebreaker about the three devils, right? The three noises, the 1F noise, and the drooping noise, and the mandrake. And that's what I meant here, the sound of demons in devices and packagings. We're talking about the MIM. Why MIM? The metal insulator metal. This decoupling capacitor is, I call, expensive earmuff. Earmuff for shushing the noisy demon. Shh. The noisy demon. You heard the three noisy demons that I presented as our icebreaker, right? And I want to compare the top three, foundry in the world, IBM, TSMC, and Intel. Samsung, on the other hand, is pretty much similar. So no point of discussing into that. And they have very limited information about the MIM they use. And so these three companies are more interesting to me. Now let's come back to our topic. The noise. I call it the sound of demons in devices. You heard the 1F noise, which is the pink noise, or called flicker noise. Pretty much it's like it's for example, it's an electrical noise generated from the defects, IKIL, right? Now the defect at the interface can talk to the device. So in turns, it generates noise. Nothing is flat like this, right? It always has some noise. And the formula for the 1F noise, why it's called 1F, comes from this. The frequency of the noise comes from the device, some constant device by the COX device, by the device dimensions, the width times length, and times the reciprocal of frequency. That's why it's called 1F noise, kind of a low frequency noise, right? It's not that high frequency. That's why I call pink noise. Pink noise is in the noise spectrum, somewhere you still can hear it. It's so high noise, you cannot hear it. That's, kilohertz, you cannot hear it. And here, pink noise, you can hear it. And today, our focus is not in 1F, right? It's just a comparison. It's just for you to, and FYI. Today, I'm going to focus on the drooping noise. The funny drooping, the voltage drooping. It's from the power transient related. And they sound funny. It's from the output voltage loss from device driver load. When a device, you turn on a device, when they are driving a load, and something happens. They don't have enough energy. The funny thing is, not enough aphrodisiac, trying to make fun of it. Why I have that comment is because this. The noise, the history, from the mythological world, the most famous noise is the mandrake. Mandrake is look like a plant, right? When you put it, I'll show you what it looks like later. You make a shrieking noise, and it will break glass and kill a person. You hear a mature mandrake. Oh, that's what J.K. Rowling say, right? In reality, it's not true. It's just a fantasy world that she concocted. She's so imaginary, so innovative. If you look at the Mandrake legends, the Mandrake legend, Mandrake, if you do the etymology, it's man plus dragon. Drake is dragon. Some people know, and the last name Drake. That means dragon in ancient time. It's also the name of Abdulu. Abdulu is devil's testicle. This is an ancient mythology aphrodisiac. It mentioned in the Bible, by the way. So don't mind, I just make fun of it. No wonder they shriek when pulled hard. Right? Try to make fun of it. If you look at this, what's this? This Chinese ginseng, right? Chinese ginseng look like a human baby. Look like this. And Chinese ginseng is also a well-known Chinese aphrodisiac. Only rich people can afford to buy it. Okay. Now they grow in Wisconsin. And so the noise. Here, my point is that noise is the sound of demon devices. There are many noise. And noise in everywhere. Here, I mentioned this before, right? Shannon information entropy. Maxwell demon inspired Simon, inspired him to come up with this, meaning that there's always an overhead in transmitting any information. It's demon at work. Same thing here. You want to do something with an electronic device, it will come with a cost. It will come with a noise. And here, see, you want to apply voltage to you want to drive something. You put a voltage there with your power supply, and that's what you expect to have. That's what you like to have. But you never get that. You will see a drooping. That's normal. And that's the noise I'm talking about. That's the overhead transmitting any information. And later I'll go deeper into where are these noise come from. And in the Shannon theory, he even have a formula for that, right? The maximum capacity of a channel that could transmit any information is just the number of channels times the bandwidth, and with the signal to noise ratio in a logarithmic scale with a base of 2, right? So there's you go. There's a noise, signal to noise ratio. And that's a formula he eventually derived, coming from that he derived. And so the bottom line is, noise are demons asking for ransoms. Remember the movie? So good movie. What I meant is that the randomness and chaos in every physical phenomenon, and transience in every operation. You have this transience in every operations, every electrical operations. And energy come with entropy. Energy is what you want. Say, I want to draw a device. But when you spend some energy, it'll come with a cost. It'll come with entropy. And at the end of the day, you need to pay a hefty ransom. You need to pay a lot before taming the demon. In our case, in my talk today, is a costly MIM, metal insulator, metal decoupling capacitor. Okay. Let's look at the circuits. That's when you run a circuit with a loop, right? What I meant is a loop here. Here's a loop. A loop, meaning that this is a load. So when you want to try, so this is your low capacitance, the total system. So you have a CMOS and many circuits, and you want to turn on something to do something. Then you apply apply voltage VCC. You apply a voltage. You see it create a loop, right? And what happened to the loop? Loop is that it involves many laws. When you're flowing a circuit current, generate a magnetic field. When you flow something through a loop, it generates a magnetic field. Right? That's the Ampere's law. That's Ampere's law. Then this magnetic, when you have a loop, this magnetic field enhances the magnetic flux through the loop. And when you, and that is that's the loop formations. At the end of the day, you will see when you, okay, this hand is putting a magnet through this wire, right? When you put it in and out, you will feel a force in your hand. You will generate electromagnetic force opposed to change of current. When you want to push it hard, you will feel a resistance. When you want to pull it away, you will feel attraction, you want to come back. So you always go against your will. That's the message of this curve. A demon always go against your will. And that's what happened. That's what happens in our circuits. And so that leads out. So with this in mind, let's go to our basics. The metal insulator, metal, this kind of, it's just capacitor, right? Except the electrode is making this metals. The definition of inductance. The inductance is that when you have flow something, the inductance is a magnetic flux going through a loop divided by current. The loop area divided by the current. That's it. So there's an induction coming along. You have a cell inductance and you have a mutual inductance, right? And this cell and mutual inductance plays a role in our noise. This is what I meant by the noise that we're going to talk about. The drooping noise from the power supply. Okay. And the loop inductance of the equivalent circuit, the one we're showing here, is like, that's what you have. You apply a power supply and you have a ground. And eventually you will come with a loop. And basically, this circuit is come from this picture, right? I think this is a better picture to explain that. You have a load, which means that the thing you want to try. And when you put your VCC, your power supply, on top of the load and try to drive it, you find out you generate your on and off, right? You generate on and off. You feel a resistance. Something is wrong. Right? If you need to turn on many things at the same time, you're in deep trouble. Because when you're switching from a high to low, a voltage develops in the ground plane. You always you see a voltage shift. And so when you do simultaneously fast enough, you will see a noise. Because ground plane noise become a problem with your signal integrity. So it's so sensitive. You're on and off. If it has a voltage shear, then the equivalent circuit will tell you that, oops, right? You have a problem here. This go against your will. You cannot have a constant here anymore. The loop is equal to the L1 plus L2 minus 2, 1, 2. This is mutual inductance. What I meant is this. L1 is your circuit, and then the L2 is your ground. So that's your ground. Here. L1 is a signal, and L2 is ground. And then mutual, right? So you have two. And then your voltage is transient, is your inductance EI over dt. And that is your voltage. So you will see a change in your actual circuits crossed L1. And they come up with a term. It's called SSN, switching simultaneously. This kind of the SSN, this value, this SSN means a switching simultaneously. This noise, you're coupling to the everybody around it. Imagine if your low capacitance has a lot of circuits, this is your die. And then you have many things to turn on at the same time. In your cell phone, say, hey, I want to play a game now. So I go to the website and I click turn on the game, or I have a game installed in my cell phone, I play it, or my laptop. Well, things get heating up. Power get coming in. And you will see SSN increases. And very, very high noises, your power supply should collapse. If you have a lot of SSN noise, your power supply actually cannot support that, and it will eventually collapse. So that's the problem, right? That's what I meant here. And L2 ground, so L2 ground and M12 is where you generate your noise, because your energy cannot be, it takes energy to turn on, and then there's a price to pay for that energy. And then it cannot currently turn off, because nature says, no, you don't go, right? See here? See here? I want to put the magnet in. They will push back. The magnet said, no, I don't. So these magnets be pushed back because these circuits. So you say, no, I don't want to come in. But you force it in. So you spend energy to force it in. And then you want to take it out. I said, no, don't go. Okay, don't go. I want you. So you always go against your will. The demons always go against your will. And that's sort of what's happening here too. So I wanted this, when I don't want you, the off should be just off zero. But off is not zero. There's something there. And I will turn into a voltage. So, and then you add more. So I will turn on, at gigahertz. Oh my God. Then that's trouble, right? Then you're in trouble. So that's the reason why high SSN, the power supply, will actually collapse. All right. And the SSN simultaneous switching noise is just, your voltage difference divided by the parasitic inductance. It's a parasitic one, right? Everything parasitic, meaning it's controlled by demons, to me. Yeah, the price you pay, right? The ransom you pay. Remember the ransom story? You had to pay. Yeah, everything transient. Energy comes with an entropy. You pay a hefty ransom for the single thing you want to do. When you want to do something, there's always nature want to go against you. You want to do something, they say, no, I don't want you to do it. Okay? When you want to come in, say, no, I don't want you to come in. When you say leaving, no, I don't want you to leave. Always go against you. Always go against you. And that is a fundamental of the noise. And so this is what I meant. When you see parasitic, you see demons. Right? And you look at this is the 2020 TSMC paper, co-author. It's called deep trench capacitor. It's kind of an MIM, but in 3D in a deep trench like memory. This is what they do, what they have done to their packaging to support their HBM2E, high bandwidth memory 2E, second generation and this is extended, so it's 2E. At 3.2 gigahertz. See, they could generate, this is the big noises here. The big red noises here. They could reduce it like 60%. That's achievement from this process technology. MIM, metal insulator, metal decoupling capacitor. They put a capacitor in place they need in order to reduce its noise. That's pretty much it, which means they store energy at the cost of real estate, right? They take out, they open up space in their circuit, say, oh, I'm going to put something here. I'm going to store it. So when you need it, I'll give it to you. So they're paying the ransom on site, right? And this technology is not new because we saw that in our pulse drooping in RF, right? RF is just like this. This is what you want. Turn on and off, right? This is what that's what you should see it. But you don't get it. You don't get it. You will always get this noise, this drooping noise. Okay. The pulses change in the shape of signal because you want to have a transient, a variation of amplitude of signal from its baseline to a power or higher level. You want to go like this, is what you want to do. But you never get that shape. You want to get a constant here from your circuit design. This is what you want. And and this is so clean, you'll never get that in real world. You will get overshoots and come down a little bit, and here is too low. You always pay a price because of noise. And then your signal lost stability. If you cannot pay them in time, you have to adjust them in time. So I don't want this too much. So how much is too much? And there's a spec for that, right? And if you look at any circuit's PDN, power delivery network, you have a 12 volts from your power supply, and you cross the motherboard to a voltage about 1 volt at a die. That's what you usually have. Actually, it's lower than 1 volt for the say 7 nanometer or 10 nanometer below that 0.7 volt is less than 1 volt when you apply to a transistor from the top down. You change from 12 volts to 1 volt roughly. And you want to turn on and off. Meaning that there are many, many gates begin to switch. So the current draw will suddenly draw, right? We're talking about gigahertz, right? It will draw suddenly. And it will cause an immediate droop in the voltage across the chip. It's called first order droop or first droop. And then you interact with each other, right? You interact with the whole thing. You get, so these are first order and a second order, a third order. And this is a voltage and impedance change from a standard operation of switching. A digital circuit, even analog, it just try to search just 0, 1 or high, low. That's what you want to do, right? That's all what you do all the time. Except you want the power delivery network to give you always a perfect one. Don't give me noise. And in a worst case scenario, the first and second droop can drop voltage by 10 to 15%. Is that big deal? 10 to 15% drooping, meaning that you don't get what you want. You get something less, like 80%. Maximum 90%. 85 to 90%. Is that good enough? Well, if you look at the new node, so TSMC announced they have, I have a new node, 2 nanometer, improve better than 3 nanometer in terms of performance. It's only 15% all around it. 30% is kind of exaggerating. You get about 15, 20%, that's you consider pretty good. And that because and then with that, you actually spend all the money. You buy a lot of additional EUV, these fancy structure from FinFET to nanosheet and all that blah blah blah. You get only 15%, 20% boost. And here, if you don't take care of this problem, the power supply, the PDN power supply, the power delivery network noise will kill all the benefit that you harvested by changing A and B. You eventually spend so much money, and at the end of the day, you'll be eaten up by this noise. You pay the ransom. Right? You pay the ransom of the noise. And so that's what I'm going to talk about today. So how do you do? What do you do? How do you compensate, reduce the effect of this drooping noise? And that's the main goal of this talk. And it turns out that more complex system, the more noise. High-level integrations right now, the high-level integration is inherent with multiple noise sources. You have a mixture of IP, a power supply. The system getting the SoC become more and more complex, right? The more complex the system, the more inherent noise sources. And the genius IBM apply MIM to dampen out the power supply transients. Here example is 2007. This is what it did. Put a here. This is your power grid, right? This is the one you try to overcome. This is a power grid. It gives power to the power to the power rail, and upper and lower power bus. The whole thing tries to supply power to a transistor, and it has a lot of noise. So the idea is to give it a MIN capacitor, and usually the last metal layer. And this is kind of a 90 nanometer SOI technology. It's an on-die MIM called on-die capacitor, ODC. We'll talk about that later. And you have a unit of a femtofarad micrometer squared. It's 8. Reasonable good. It did its job then. It's formed by what? So, I mean, our talk is our title, right? We're talking about process technology. So everything around this talk on will be focused on process. Right? And here, it's done by PVD, hafnium oxide, and tantalum oxide dielectrics. So this is the oxide they use with tantalum nitride electrodes. These days, the most I saw is high nitride. That time they use tantalum nitride for pattern reasons. These two nitride are similar, and they're both very useful with similar properties. They are all very good electrodes, and those they could be etched up to each other. So tantalum nitride and titanium can be switchable, and you just need to know which one you want and what kind of selectivity you want. And we don't use tantalum oxide anymore. I think hafnium oxide is the one we go, and we now move to aluminum oxide and zirconium oxide. Tantalum oxide is kind of not so popular these days. Okay, so IBM, the early one I saw with this a metal layer, there's a lot of last metal layer. Okay, and it did the last layer with a capacitor here. Very nice. And TSMC come up later, right? That we know. So the end of the day is try to reduce this voltage drooping effect. And the net effect of this voltage drooping is that it will add system power overhead. So you are taking ransom, say, well, you are taking 10 to 15% of my power, then I'm just going to add more. Well, can you do that? That's not a good idea, right? Right now, these days, especially AI, the power supply is a bottleneck. I saw the news that a lot of big company they want to build nuclear reactors around their data centers to supply the power because it costs so much money. So a 10, 15% error on the power overhead is a no-no. Okay. Or say, well, every time you switch too fast, noise too much. Right? Why don't you reduce your operation frequency? Well, you could do that. But do you want to do that? Right? You don't want to do that, right? Yeah. Here we mentioned this 3.2 gigahertz. As he said, I don't need to avoid this, but reduce it to 2.8 gigahertz. Well, then you lost the breaking rates performance. So you don't want to do that. Or you impact reliability and functional safety. Yes, you will. The transient across system is a performance degradation and then reliability issue. For example, the noise we introduced very early. This is a reliability issue. 1 amp noise, very famous. The defect noises, the electrical noise generated from the defects are very important reliability issue. If you get too much of it, you kill your dielectrics, you kill the device. You shoot your VT, you're dead. Okay. And so, bottom line, no, this is not what I want, right? Yeah, not what we want. The sound of demon device. We don't want that. We pay the price. We have to pay elsewhere. I don't want to pay by adding more power. I don't want to pay by lowering my frequency. I don't want to pay with my reliability. No, I don't want to do so. Okay. And so how do you do it? Well, you could use software tweak, NG Streamroller. It's a tweak, a software tweak. It says that, oh, there's some noise because you see a drooping. Then you say, oh, okay, I'm going to reduce my frequency. I'm cheating the system. And then if the noise come back, okay, then I will come back. So I mean that I slow the clock. This means that I dynamically reducing my operating frequency. So I hope the user don't notice it. Well, it's okay. It's okay. If the problem is not too severe, you can play the game, and it adds some. I think it'll save you that 5%, something like that, maybe. And that's good, but inadequate. I'm sorry to say that. It's just not enough. If it's enough, there will be no MIM in this world. And you look at TSMC, see, he damped down this voltage drooping, right? This one 70%. Wow, the voltage drooping damped out 70%. Very nice. And the impedance much, much lower. Okay, 90%. Oh, okay. So these are all this in frequency domain, and this is in time in this voltage domain. And they use a deep trench MIM called ICAP. This deep trench capacitor, meaning that they make the trench instead of making a transistor, a plate-like transistor. This is a plate-like, right? This is a standard capacitor look. It's just a plate. And they're using a deep trench, which I introduce you later. And they did a good job. So net, MIM benefits at cost. There are a couple of parameters you're looking at. high capacitance density area. The femtofarad per micrometer is the unit used. And you want a low parasitic and high C. And the C has to be independent of voltage. So you use metal layer. Metal layer means that the voltage can directly apply to the capacitor without going through, suppose you use a semiconductor, then you have a depletion problem, right? So you use a metal, so the voltage will immediately across. So that's why it's a low parasitic if you use MIM. And of course, you pay the price. But the price you pay, additional mass and process. Okay, look at this one. This one, this extra, meaning there's an extra mask. Maybe one or two, right? Because this one's a normal pattern. And in here, you have to insert something. So this is extra mask, at least extra one mask, maybe more, to create this structure. Now, imagine if I want to create a trench. Oh, that's a different story then. We'll show you later. And this is XFAB, XT018. Okay. And then it has this density about up to 6 femtofarad per micrometer squared. TSMC 18, about 1. Okay. It's their technology. They use a planar MIM capacitor. This is the normal use. It's still being used today in most devices. But here I'm focused on more advanced. So before I go compare, I want to compare IBM, Intel, and TSMC, their MIM family. I want to give you a simple summary. MIM is your costly Gucci earmuff, right? To dampen the mandrake noise. Should I say dampen? No, I should say swish. Let's change it. Shush. Am I correct? Right. To shush the mandrake shrieking noise. The noise is shrieking. It's a shriek. Right. So people have to put an earlobe there. Okay. And this is matching to my title. Yep. An expensive earmuff to shushing the noisy demons. Yeah. So we talk about the basics, and then we give you some examples, and then we come to a conclusion. Yeah, MIM is your costly Gucci earmuff. It's your Gucci one. It's not cheap, okay? It's never cheap. And we'll see how the world fares. And I will introduce the KPI for this. Capacity, you need to have adequate capacitance density. You need to meet reliability spec. Of course, as cheap as possible, meeting goal, meeting spec. And you need scalable to next node. So this is pretty much the KPI, the key performance indicators for the MIM. And later I would like to compare IBM, Intel, TSMC, their MIM family. First, I would like to introduce the mother of all innovators, IBM. So there are two types of capacitor, the MIM capacitor we're dealing with here. One is called ODC, on-die capacitor. The other one is in package. There's no on-packaging capacitor per se, but let's go through one by one. So the first example I mentioned, I want to do IBM first. But this one, let's start with this introductions, 16 nanometer. I don't think it's IBM. IBM, does it have 16 nanometer? Questionable. But anyway, It's the same thing we mentioned here. It has the last metal layer. So this is a last metal layer to put a capacitor here. And here's just an example. I want to show a schematics of it. Okay, this is capacitor top metal, top metal plate, top metal electrode. This is a capacitor bottom. So usually it's M12 and the 2 Intel and N11. So it's inside the V11, the VR11. Usually that's where it hides. So the top metal and bottom metal, and then how you're going to put in between, that's your good business. And they are made from aluminum, copper, tinitride. These days we do ALD tinitride a lot. Okay. ALD wise, we have silicon oxide, nitride, hafnium oxide, aluminum oxide, zirconium oxide, etc. So you can see that easily could do to a mole mask. That's where the cost come in. Come back to this IBM again. So it's a 90 nanometer SOI technology. And that time, I think IBM is the most advanced in the world at that time in terms of process. They don't have a high yield, but their process are much more advanced. For example, they're about at least 3 generations ahead of Intel in terms of copper. They adopt copper technology much sooner than Intel or anybody else. They're very innovative. And that's the strength. So there's no question about it. So this is what time? This 2007 IRTC paper. And this is where they put the capacitors, right? That the capacitance density is 8 FF micrometer. So they keep it in mind. This unit is important. Then later on, I found this 2016 INCAP. And here is more interesting. This is Endo. Oh, one of the colleagues I worked with while I was at a project with IBM. It's such a innovative engineer. I think he's kind of a master these days, meaning that you have a lot of inventions. In IBM, you move up in the rank from the process side, you move up into this master or innovator, and after your senior engineer role, and you want to become a fellow. And here is what he has done. There's many innovation on this the MIM area. And these are schematics of the 3-plate MIM capacitors. And he has up to 43 now. Well, that's pretty good. His leakage is reasonable. And I think the achievement is that's ultra thin 0.8. You want to have a very thin EOT in order to have a large CET, right? You need to have a large capacitance. And of course, you can see that you have 2 there. He has a 3-plate planar structure. It's close to Intel did later on. We're going to go through one by one. Here, I'm just going to do the evolution of IBM technology. So this is what they achieved, right? Go to about 44, right? I found this figure, 44. Of course, a little bit higher leakage, but if you do a low one, about 40. About 40. And they used tiny nitride optimizations. And they used a new carbon-free high-K precursors. I think it's hafnium oxide here. There's a buffer layer up and down. It's a tri-layer. And tri-layer, they have 2 approaches for this. One is buffer layer, top and bottom, and you sandwich high-K here. High-K, I meant hafnium oxide. Or hafnium oxide, top and bottom with a buffer layer, something in between. He didn't tell. But later we find out what it is, right? So this is the how he achieved 0.8 nanometer EOT. Of course, with some good high-K material. And this is the process flow. Okay, you had the bottom high K interlayer dielectric disk for your metal layer already, for your ILD layer. So ID 11. High K deposition after the bottom TIN, and you have O3 anneal. The reason you want to have O3 anneal is that high K deposited has a lower atomic density in general. You need to densify the material by adding a little bit more oxygen. Okay. And then, of course, and then you put a top there. Here, TIN, you have some kind of optimization. So called top TIN deposition. And then you have a patterning, the edge. And then you're back, and then you do a final anneal. This is a little bit long, 200 degrees Celsius, 2 hours. You just want to densify the material, right? You want to stabilize this layer, right? This one. Once you pattern, deposit and pattern, put it in, you want to anneal the whole stack. The whole stack had to be annealed. And then he did anneal with 400 degrees Celsius, 2 hours. Kind of too long to me, but that's what he suggests. And if you look at, so this is what he suggested 2016. But we look at the later paper by GlobalFoundries. GlobalFoundries, this is what he did, right? GlobalFoundries on-die capacitors, HBH is this one. High K on top, and then the aluminum oxide in between. This is one of the options that in 3 years earlier that that Endo proposed, right? You could do 2 type of high K, get what you need. And then you could do hafnium oxide on top and bottom, or sandwich inside. And then later, GlobalFoundries said, oops, I think this is a better choice, which means high K on top and bottom, aluminum oxide in here is the final decision. And but they didn't say what temperature they anneal. I would say, the highest temperature, you can go over 500, right? But the back-end device, you cannot do 500. 400 is safe. 480 is really pushy. And the secret buffer layer, here he didn't mention. In here, the buffer layer, he didn't say anything. 2016 paper. But yeah, you finally, they go, Chen Guo, this guy's good too. That aluminum oxide, finally revealed. Why they use that? The reason they choose that because it suppresses crystallization and reduce leakage. So they're afraid we'll change it to something. So that's the reason, but I don't think that reason is real. I think aluminum oxide is there for eliminating, for reduced leakage and provide by eliminating conductive paths. So this, I believe, is true. This one, question mark. But that's what they say. Each layer, you need to really experiment, right? And people are experimenting with different high K, different precursors, and try to find out which combination is the best to give you the highest capacitance. And more process learning, right? He has more process learning. And at the end of the day, this is what he learned. The metal one, you like to have a thinner bottom electrode. I'm sorry, thicker bottom and thinner top. SX here. They did a split. S represents split. H plus 15, all right? And then IK is thin. So, and then aluminum oxide is still thick. But if they have a thick bottom, it's supposed to be the best for leakage, for reliability. All right, the top is not, the message I think is the top is not important as the bottom. So the bottom electrode give the best reliability results. So this is the on-die capacitance, on-die capacitor that developed by IBM. So later on, Endo did it again, right? And he mentioned it that MIM also needed in packaging. See that? That everything here, almost board, everything here, decap, okay, board decap, on-chip decap. This is ODC we mentioned. Inside the chip, outside the chip, inside the packaging, everything. If you see a voltage drooping issue you like to resolve, you need to add the MIM here. So takeaways, whenever there are voltage drooping concerns, you need MIM. So right now, interposer MIM, it is expensive earmuff. Is a current trend now. And MIM, they also go from planar to from the planar structure to DTC, the deep trench, right? Deep trench capacitor, DTC. See that? Why you want to go deep? Because for the same surface area, you got more capacitance surface area, but the same layout, I would say. But the same layout, the real estate on top of the silicon, you got more surface area, and that is the reason you want to go to deep trench. But GDC increase C with more area, so this is just a formula for it, right? C is epsilon A divided by D. D is the thickness. You want a thinner, the better. And this is the actual process. So the TSMC, right? TSMC, and this one is I think it's Intel. So Intel 4, TSMC, ICAP, GDC. They have a 4x of improvement in terms of area. Therefore, their capacitance density will be increased at least 4-fold. And if you look at who developed DTC process flow, again, IBM. Because IBM did it for EDRAM. They are very ambitious. We're very ambitious. Say, I want to put DRAM and my device in the same die. Oh my God, that is very ambitious, but very dangerous. Okay, they want to do this. 40 nanometer FinFET, SOI, and all SOI, it's everything, pretty much everything. And then, of course, fails. Sorry. And then use EDRAM is L3 cache, right? L3 cache. And this is what they had proposed to do, Power 8.9. They could do it. I mean, you could always do what you said. It's just whether the yield is good enough. All right. That is at the end of the day is, can you do it cheaply and in a profitable manner? But that's what they showed that time. Or the Power 9, very famous Power 9, 14 nanometer. Did not go very high volume. I'm sorry. And then the IBM, I mean, IBM is true DTC innovator, right? They give you process flow. So how do you do it? You know, this is the process flow. How do you do it? Because they use the EDRAM. EDRAM has the same structure as the MIM, I mean, as the your on-die OTC or on-die capacitor, except that they may be a different dimension, but they are the same in terms of structure. It's just a DRAM structure, right? Deep trench capacitor, and then this the real structure is used for EDRAM. So, and then they give you these process flow. And this is not too far away, a little more complex than what Endo proposed, right? If you look at the Endo's process flow, Endo is just a simple capacitance flow But the idea is there. They don't have a trench. But the idea of selecting high K, because that's what Intel is focusing on. What type of high K, what type of high stack you want to put it on. Here, of course, you have the pre-clean and IL, and then surface treatment and high K depositions. And then you have PDA. And because you have done it not at the end, this is the beauty. You're done at the beginning of the process flow. You didn't do your EDRAM at the metal 11, right? You did it at the ground floor. And right at the SOI. And so you could afford to have a very high temperature PDA, the post-dielectric anneal. I mean that you are annealing your high K as high as you can to densify the high K, to measure quality, also the facial layer better. And you need pretty high, 800. Could be with a laser, could be with a flash, you don't know. But you need to work on it, optimize it. And then this effective work function tuning. And you put a stressor, that's how it's going, right? So, but this is the EDRAM at the beginning of the process flow. Right? It's always right here. So it's at the bottom layer. It's 2012. So they already started developing this. You see, that's why I always say IBM is a true DTC innovator. They always come out with the technology that's the newest at the moment. And IBM 22 nanometer ODC went deep trench. Okay, they took the idea and then they do a deep trench. Okay, deep trench for the EDRAM. This is 2 years later. These 2014, right? They show exactly how they did it. And then, of course, they have more technical content inside. They put the stressor here, right? The silicon carbide stressor on the NSD phosphorus. And this one work on the IBM, but nobody really uses it because when you put carbon inside, you increase the stress with tensile stress. But at the same time, you increase the resistance if you don't do it right. So then you got less voltage across it. So you lose a dry current. You could improve the mobility, but you lose the dry current. So net, no good gain. So these days, I don't know who is doing that besides IBM. But as again, IBM is innovative. They do everything crazy. They want to put all the new things they could think of on the periodic table, on any idea. They put it there. I respect them for that. And then the ODC, they put ODC eventually in deep trench in 2016. For the 16 SOI, the deep trench capacitance not as the, but this is, I'm sorry, this is the ODC, right? And pretty good job. I would say pretty good job, capacitance. It's not an EDRAM, but it's ODC. And all these, they publish it. They will publish the result and say, this is what we did. And you could analyze, they are not afraid of copycat. And then the process learning are captured by others, meaning that Intel, TSMC, and Samsung will look at it and say, oh, okay, it seemed that they could do it, meaning that it's doable. Even that learning is valuable. And the key message that I would like to share with you is IBM has never been afraid to share their knowledge. The others, I would say, the other way around. So I would say they are most innovative company in the world. They're number one in patents. The number of patents they publish every year is 3 or 4 times more than Samsung and TSMC, Intel. right? Combined, that's how good they are. But they're just not good at HBM with a high yield. That's because the engineer all want to be a fellow, want to be a master, and then so they could do whatever they like, which is now they're protected. They have a good life. In Watson, I visit their beautiful facility. Everybody got a ranch home. They live comfortably, and then they are the greatest scientists in the world, which I believe so. But they're just not good at making the high yield because yield is another animal, right? You got to go through very detailed in making sure every step are super clean, and they are very have a high process margin and all that. And IBM, I'm sorry, they're just not good at that. Okay, because they give you a new idea, they prove it work. Just like the Endo, right? Endo say, "Oh, I give you this idea, go innovate and make it 100% yield. And just give you this idea. You go figure out yourself." Right? So that's their mentality. And then let's look at Intel. Intel 22 nanometer MIM, they have it's type of OPC. People say they have type of DC. Okay. And they have EDRAM in metal 2, metal 6 layer. This is what I found out. They have some EDRAM inside. Okay. That's what these reports says. I'm not 100% believe that, but that's what they say. Because I think you want to do EDRAM, you need to make a large, right? You just don't make a little bit. It doesn't make sense to me. But meaning that I'm a process guy, so they just look at process flow. Okay, they could do it, right? And then they have extremely thick. They have this extremely thick top layer parallel metal plate. Okay, fine. Not this one. This panel plate. I mean, ED for the this is not ODC. This is the MIM. This is the EDRAM. This is EDRAM. Okay, this is EDRAM, right? And they have this ODC in a metal 11, metal 12 layer like this. This is what I meant. Okay, and they say the top layer are very thick. Well, the same thickness here I see. Maybe. And then it's called triplate. They go only triplate. And then use TIN. And then just use hafnium oxide. This is all typical semiconductor process tool we have. And triplate, that the number they finally come up with 40. They're 40 nanometer, yes, pretty good, very decent, number one in the world that time. They are indeed number one in the world. Nobody can beat them. The other 40 nanometer, they hit it first, they run it, before Samsung and TSMC catch up later, but that time, they are truly in the world number one. And Intel ODC, 10 plus nanometer, they make it more complex now. There's a 4 capacitance layer, 4 layer, okay. And this is what they 3 plate to 4 plate, and then 3 high K, hafnium oxide, aluminum oxide, and zirconium oxide. They have more combination of different high K. And they have variety of min cap density, 37 to 52. And this is reasonably good. And 4 plate one, they go to 141. Very decent, very decent. So the 52, 37, okay. So this is what they come up with. And they use a mixture, see that? Well, this time, I must get into that. They give the detailed description about the high K they use. Again, aluminum oxide, and then zirconium oxide. Why they use the different oxide with different high K? That I don't know. It could be something with the process that in a way that they find out this combination has the highest reliability. You see, Intel would try everything. That's their mentality. They know that this every high case, the aluminum oxide and zirconium oxide, in addition to hafnium oxide, each one has their benefit, right? Hafnium oxide is your baseline, so you use that. And then you use aluminum oxide probably because it's the lowest leakage. And zirconium oxide, you use it because it's a lower crystallization temperature. And you mix them, and then you see what's come out, right? I think they did a lot of DOE for that. Just like the high-tech metal gate, right? They have a lot of metal gate options. Eventually, they find out aluminum will work best. It's just by experiment. Well, that's the beauty of Intel. And if you look at the pattern that time, this is their pattern. I found out this pattern matching this very nicely. Similar author, I would suppose. The author is also part of the paper. So I think they took this seriously. And this is the A1 pattern. A1 pattern meaning that it's really serious. All right, if it's something else, B1, B, A2, it's good, but not that. A1 meaning that they are serious about this. So I would say this pattern is serious. Okay, so they are 10 plus. Well, they failed 10, but they succeed in this, right? Don't get me wrong. And then this year, they make it vertical. They change this to a vertical structure. And you can see this, see that three metal layer, and this is three metal layer. They just make, the way I see the Intel TTC is they're planar gone vertical. That's what they did. They make it a vertical. And then they improve, of course, their total capacitance here. This is the combination, the highest of the world now, right? This is the highest. The TSMC is not as high. We'll do a comparison later. So the message that I conveyed to you that not just this is the sort of this OTC now, this MIM moving to packaging, and they use the they use not OTC, DTC. DTC is the one they use to make packaging. This one is Intel's Foveros. The Foveros. This is packaging, and this is one that show how exactly they did it. All right. So this is one in this packaging. It's a metal 2 and metal 3. They put a lot of MIM cap here. They call high density MIM. And this is obviously a GTC. So the message here, whenever you see a voltage drop concern, you need MIM. Anything you see, there's a drooping. There's the voltage drooping, not drop, drooping, sorry. You need MIM. Everybody said the same thing. TSMC, of course, 100% agree. They did it too. No surprise. So what exactly to achieve then? You can see that with or without the deep trench capacitance in their packaging, the performance is kind of night and day. You look at the voltage droop, it will change from no black one is no MIM, drop to the green one with trench one. Planar drop a little bit, not good enough, and then now you drop it to with a HD MIM, high density MIM. It's kind of DTC. You drop to original, like you improve like 60%. For the voltage droop issues, you improve hundreds of millivolts. Right? You without droop is 196, and then with droop is 122. So you improve 55. I'm sorry, not 100, but 55 millivolts. Okay, that's how you could. That means the less drooping when you supply your voltage from your Foveros to the dot. And reliability is good. All these are good, no matter what you do. It seemed to me that the MIM reliability is usually not a big deal, meaning that everybody can meet it. If they cannot meet it, they tweak a little bit, then they can meet it. All right. There's 10-year time to failure with a whiteboard curve, and you had to be below it. And then so it seemed that I could do it right. And I found out there's no reliability issue ever reported by foundries. I mean that, of course, they want to report it as a problem. But what I meant is that they will not make a big deal out of it. They say, oh, yeah, it's good. Yeah, yeah. The fundamental is that it's not an active capacitance. It's a passive one, right? It's not like your transistor is also a capacitance, a capacitor, because you're modulating. And that everything is important. And here is not that. So your transistor is an active capacitor with a gate control. But your MIM is not. It's a passive one. And they are positioned very far away from sensitive transistors. So the position is very far away. So they're not supposed to do any VT change or something like that, right? So they're fine. As long as you do a decent job. Decent job. So all the report I saw, it's reasonable. No big deal. And so I want to see what is the best-in-class comparison. Intel is the best-in-class for CD, the capacitance density. See that? It did. The one I show here, 376. This one. The sum of them is 376. See, Intel 4 did a pretty good job. And what about TSMC? I would do a heads up first. This is what I found later on. They just announced this 200 nanometer. This is about silicon interposer. 2 nanometer. 2 nanometer one. They come up with 200 exactly. Okay. And ICAP, they have a reported value like 340. Pretty good too. Right. So, but overall, Intel has the best process technology in here. That's their one of the competence, but that's not core competence, I would argue. It's good, but that's not the reason to make them great yet, right? It's just good enough, it's good enough. The reason is that Intel, they fail at 3, or they fail at 3, they say I want to manufacture having my chip 3 nanometer goes to TSMC. They cannot make it in time, whatever reason they come up with. They want to focus on 1.8, right? I don't know why, but that means that their packaging, I'm maybe good, maybe they do own their packaging, but that tells me that there's a concern. So that's the Intel. Let's look at TSMC. TSMC is famous for its cobalts, chip on wafer on substrate. And then they put it, initially they put it just like everybody, metal tool, okay, here. Inside a metal tool, they had a CTM, capacitor, top metal layer and bottom metal layer. IK between. And this is, they hide their main capacitors. And what they come up with this paper is that their EOT is not 0.8, it's 2. Reasonably good. It does not really matter. It serves their purpose. But I think that one outstanding one is the extremely low defect density. D knob is 0.09. This is much lower than reported on the actual die one. I mean, actual die one is like, I'll show you later, 0.8, less than 1. But 0.09, this is really good. And this good low defect density to enable their large silicon interposer. I think that's the key. So I could do capacitance and pattern them and put MIM there. Fine. But you need to do it extremely high yield. And nowadays they're doing the CoWoS even rectangular one. The substrate tends to rectangular, and they're doing the 7 to 8 radical size. This is not that big yet. This is really big. Okay, much larger. So, and the reason I keep emphasizing on the yield, because that's what differentiates TSMC against Samsung and Intel. And look at that, why I said this is extremely good value. I use examples. I calculated that TSMC reported that yield rate is about 80%. This is just hypothetical one. Close, it should be higher, maybe 90%, but let's assume 80% for the HBM data. For Apple 13, the die size is about 1:1, 1 by 1 centimeter. So question for you is that, what happened to yield rate if the die size changes? So this one, I'm going to take it at D-naught. D-naught first. So I use a Poisson model. Poisson model yield is exponential this. Area times D-naught. And put it there, D-naught is 0.2. 0.2 centimeter squared. And then this is negative binomial distribution suggested by ITRS. So this is if you have 1, 80% yield, if the die size is 1, then this is what it should look like. Larger the die size, the smaller the yield. Right. And from this calculation, I would like to share with you is that the D-naught I calculated for 80% yield with the die size this size is 0.2. And if you look at they reported D-naught is 0.09, meaning much smaller. That means that the yield rate is much larger, right? I mean, you look at this Poisson model, exponential, smaller this number, this one close to, and then this one holding close to 1. Right? So this is what I meant. D-naught is very small. Yeah, that's the beauty of it. Theta it's at least 1 order of magnitude, close to 2 order of magnitude smaller than this value. 0.2 is 80%. I would say 0.9 with a similar idea should be 95 or 99%. Oh my God, right? So this means that 0.09 or 0.095 centimeter D-naught, meaning very high yield. I would say almost 100%. Okay. And so it has a reasonable cap density, low leakage. See here, low leakage. And the distribution is very sharp. Look at how sharp that is. The slope of this is very steep. So your cumulative distribution curve, when you plot it against some functions, and we talked about this in our last conversation, last talk about reliability, right? The sharper, the better, and there's no kink inside. So they reported in this paper, all right? This is one of the early one, and then this is 2014, and then they have up to 17 FF micrometer. Okay, but what's the average of them now? It's difficult to see. I don't know exactly distribution of the 3 type of capacities. This is not a deep trench. This is still irregular planar. It's just making more layer, right? And then later come to the 19 one, 2019 IDM. Wow, they have the DTC now, the deep trench. They call ICAP. Later they call themselves DTC again, so they're up and on. It is a deep trench. it is a DTC, but that time they name it ICAP. Okay, everything you want to name I for fancy. And this is one they shown below M3. Okay, and if you compare with okay, M3, and then this is the one I show here too, M3. This is a TSMC picture when I compare. And the result is that a 55% reductions. They're quite 45% or 55%. Anyway, around 50% reductions. Oh, here, I'm sorry, it should be 45% with ICAP, deep trench. This is one I'm talking about. I put it here, silicon inside silicon interposer. I didn't mention they put it in other packaging. They should, maybe they did, but I just don't know, right? They didn't say it. Because as I mentioned in the earlier introduction, that a thing go to packaging. Everything go to packaging, right? You need to put in everywhere if you find out you have a problem. Maybe you don't have a problem. Who knows? And the results. Okay, no, that's it. That's right. These results is 45% reduction in the voltage drooping. And then you could use that, see, then you look at the pattern that time. Yeah, I kept the same as here. Very similar, right? Very similar structure for their patterns. The idea is that you need to protect your core competency with patterns. And that's exactly what they did, right? You cannot come up with a process flow without pattern. Then you'll be sued. Bottom line, you'll be sued, no problem. And that's scary. So TSMC ICAP, okay, this is what they did. GTC ICAP. Their standard cell is 40 by 40 micron. Density is 340. It's not too far away from Intel 4 376. And it's 200x of high density MIM. Total capacitance 68 microfarad per silicon interposer. So these are good values to meet their demands. Are they going to improve continuously? Oh yeah. Oh yeah. But before that, let's look at the process flow. We were process guy. We want to know how they did it. They did say, this is the first time I saw this. they did it, right? This is how they did it. This gray part is poly, and this yellow part is the high-K dielectric. It suggests two flow. The TSV first, they put trench in first, or DTC first. TSV first because they want to avoid TSV via protrusion problem. And then that if you do DTC first, then this TSV thermal budget need to be controlled. Because you later do TSV later, then you need to watch out the thermal budget. And inside the poly with a high aspect ratio of 10. Well, this is a dummy silicon gap field, just like RMG process, the polysilicon dummy field. Pretty good, 10, reasonable. They could do it. But you need to do kind of doping, right? But you cannot use pure silicon. You need to dope it to keep your RS and ESR small. You need to keep the resistance small. You want a metal, right? You do have metal, but you still need this is your electrode now. Your electrode is here, but inside you still need some electrode to keep your ESR and RS low. So I think you need to dope it. And the other day, see that they're true. This is very nice, straight line, no serious kink observed. Yeah, ICAP, and they're very tight distribution. I think this is strengths of TSMC. If you look at the publication from these two companies, the other company never show this data or seldom show. They show something, but not too much. Especially IBM will never show that data. All right. TSMC is not innovative as IBM and Intel, but excel in HBM mindset integrations. This means that this high volume manufacturing mindset they have, a super tight distribution and solid yield. I think the bottom line, that's what they excel at, or good at. For example, this paper is interesting. They want to do the MIM capacitance, and they come up with a pattern, and the pattern says that they focus on HBM aspect. They're not doing the novelty of this pattern compounds that they have ensure extremely low roughness. The RA is less than 0.3 nanometer dielectrics to avoid the E-field non-uniformity. Imagine if your metal or dielectric is non-uniform, you of course create local E-field non-uniformity. And anything non-uniform will give you more noise. So this pattern is geared to reduce the noise, making it very smooth. That's interesting to me. Okay. So that means that they're focusing on the process improvement technology in a way to ensure their higher yield. They're not good at innovating a new idea. I don't see any new idea from them. Every new process comes out someone else, but they make it the best. That's what they're good at. And the question is that the high K, why you choose different material? Right? You have Z for this ZAZ, okay? Sandwich layer. This paper is interesting because they use ZAZ as a tri-layer. And they said that zirconium oxides, their Z, for their lower crystallization temperature. So they don't need high temperature. Aluminum oxide for lower leakage. These are all good stuff. And I think this is still evolving. That is a 2-year-old paper. But I think people are experimenting with hafnium oxide and aluminum oxide and zirconium oxide with different precursor and try to eliminate carbon as much as possible because that's a leakage path. Carbon is conductive. Any contamination in your high K kind of create a conductive path. And one key takeaway is that they're all ALD now, and they cannot share with front-end metal layer, right? This is all packaging layer. And that means that you cannot share with front-end line IK there because this is very strict contamination control. And the area is kind of okay, kind of dirty, not dirty at you, not very dirty, but the tolerance of dirtiness is much higher. So that's the cost. Okay. So currently you can see that the MIM process technology going that way. It's playing with hafnium oxide, zirconium oxide, and aluminum oxide with different composition, a different precursor, and try to improve in a way you get a little bit higher capacitance, and then the reliability issue still okay. And TNC, the early day, they had the planar structure, right? It's a planar. The highest they can get is 17. So this is a planar. They insert this one between metal 1 and metal 2 here. And this is their reported value. It's good for them, but now they move to DDC now. But suppose you need it, the process is there. Could be cheaper. And if you look at their HD MIM report data, I want to compare what exactly it meant. But HD MIM, and they don't never tell you exact number. The only number I can come out with, I can think is 200 millimeter, 2 nanometer, super high performance MIM, 200 FF micrometer. This is one reported recently. And they claim to reduce the RS by 50% against super high density MIM. And super high density MIM meaning that they are 4x of HDMIN. And HDMIN range from 1.9 to 17. You say 20, and 4x is 80. So you would say that this one is like 80 to 100. Let's put it that way. Kind of reasonable. Just my back of the envelope estimation for your reference only. And 2 nanometer, the recent announcement, I must say a little bit disappointing to me. The reason is that they push back backside PDN. In the last announcement, they would say they would do backside PDN into not the early generation, but the second generation. But they push back now. And this is because it's hard. I understand that. I give it that. I must admit that it is hard. I have a talk on the packaging technology, talk about backside PDN, and then the process difficulty. It seemed that my talk on the difficulty part is true. It's not as easy as you think. What I meant is that backside PDN and GAA is too much to ask. So if you look at TSMC, when it introduced a new technology, they introduce it gradually. They don't put everything one together. That will always fail. You look at the IBM. The crazy IBM is this. If you look at IBM, I mentioned earlier, right? The IBM. They put everything together. Wow. See? SOI, it's already hard. Sensei, hard. IK, not easy. And then the EDRAM, all together. That guarantee low yield. Right? That's not a way to go. I'm a process guy. I will tell you, you're crazy. Don't do that to yourself, right? Do it gradually. And this, I think, that's what TSMC did. Initially announced backside PDN should come out as planned, but they didn't say this time. They said something else. They said, well, I can make it up with this. I don't think it's this is super high min. Okay, and then I'm not sure it's on die. Is that on die? It is on die. I'm sorry, it's on die. And they said that they changed the aluminum RDL to copper. Here, aluminum redistribution layer. You want to make everything lower resistance. You change to copper. And this is actually a risky business. The reason is that if you change the copper, so everything is copper here already. So the whole wafer will be copper contaminated. Risky. So your microbomb here better do a good job. Okay. Otherwise you'll be in deep trouble. And so, but anyway, they seem a success. They meet their performance goal. They reduce the RS and RBL. At the end of the day, you just want system to be stable. And then you could changing your resistance. That's all you want. And reliability goal met. So, okay, this is fine. The power delivery, this one is not on die. I need to take it back. This is what it says. Let's follow the extra data. This is DDC. Okay, that's what it said here. I misunderstood. Sorry. So, copper recharge to robust power delivery system. That's what I think. And And this is I put a comparison back here. See, here is 200, and I mentioned here earlier, 200. And so this is what I can achieve, 2 nanometer, 200. ICAP is higher, but SH super high performance, SHP min 200. But it doesn't really matter. That doesn't really matter in reality. Just they're meeting their goal, right? They're meeting a performance goal, and that's enough. And so that's the best in class comparison. Intel still number one in this category, but does it matter? Probably not. So before I end this talk, I would like to give some other interesting MIM stuff. Thinnest MIM in the world, and MIM as a secondary power supply. There's a new company called Smalltech. They claim to using carbon nanofiber, like graphene. I think it's a type of graphene. And they claim to be the world's thinnest capacitors. And it's very thin, and then you can generate the highest density. 650 is almost 2x of TSMC, not 2x. This should be 3x. This one's right. This is 3x. Three X for TSMC, super high performance means shown. This is 200, right? So it's greater than 3x. Sorry. And then the equivalent ESR, the resists 40 milliohm, and then the inductance small. Breakdown voltage is high, leakage reasonable, and then stable temperature up to 150. That one's a little bit concerned, meaning that once you process it, you need to cap it, right? And then this one has a little bit question mark, because we need to anneal the thing. All these TSV anneal, everything anneal is about 400. So you stability up to 150, is that good enough? I don't know. He said they could put anywhere. You don't need trench. It's too deep. It's kind of graphene-like. We're going to make it to the mainstream. I don't know. We're just going to wait and see. Or as a MIM as a secondary power supply. It can act as a second power supply because it's rapid moving charge and high burst power. You store your charge, your energy inside, and you can put it into a flexible ultra-thin silicon fabric. You make it thin, make it flexible, so it's good for IoT and all that stuff. I think it's interesting. It's a good idea, but you don't make it cheap enough and then stable enough. Maybe that's a good idea. It's an idea. So that's what I meant. It's the other interesting MIM stuff. So at the end of the day, let's look at the MIM KPI score. The adequate capacitance density. This one, I think everybody did it. Reliability spec, everybody did it. Cost effectiveness, it's a wash because, well, you have to do it. It's a ransom you have to pay. Scalable to next node, deep trench is a goal. Yes. So the summary of this talk is that you need MIM from voltage drooping and SSN, the simultaneously switching noise. It's a demon extortion. You need to pay your price, pay your extortion fee. And you need to put N everywhere whenever it's needed, on die or packaging. And DTC, the deep trench capacitor, is the way to go. And overall, it's processed not that hard. And reliability is kind of given if you do a job right. Because they're passive. They are passive. Okay. And so I would say they are necessary but not sufficient. They're necessary evil. for your core competency. Just like Intel can do it right, IBM can do it right, but that's not good enough for them to be better than the others. Right? And same thing for TSMC. Their core competence is not here. It's necessary but not sufficient for the core competency. So that's my main summary. All right, that ends my talk. Thank you very much.